Hello, welcome back from the rest. Uh, I'm Dimitar Ivanov, and now I will talk about, Erlang and blockchain. For myself, I had been part of the Eternity core team ever since there was Eternity core team, and I have a lot of battle stories to tell. We don't have that much time though. So, what we're going to be talking today. Again, the assumption of writing the presentation was that a lot of people don't have experience with Erlang, which surprisingly is not the case. So there might be some collision with other talks before me. And then we'll go through blockchain. So, again, who has experience with Erlang or Elixir? Okay, you're going to get bored to death. Who has experience with blockchains? Okay, okay, it's going to be fun talk. So, Erlang. Disclaimer, I'm not going to be talking about the syntax of Erlang. Maybe there are some people that like the syntax, but whoever, okay. But essentially, once you get beyond the syntax, it gets really great, and you get used to it eventually. So, I have, how do I, okay. So basically, when you have an Erlang application, you have your hardware or virtual machine if you're in the virtualized context. Then you have your operating system, then you have the VM and the Erlang runtime system. And all the scheduling and all the nice things that the system provides comes from there. Then you have the OTP, which provides you with the fault tolerance, and then there is your application. In case you're into Elixir, you have additional layer of abstraction here, which implements the Elixir specifics. And if you want to be using distributed Erlang through networking, below that there is yet another layer, which is the networking layer. If you want to read about the beam and the runtime, I highly recommend the book of Eric Stenman, which is just about that. So I'm not going to be discussing what functional language is. My assumption is if you're here, you already know what that would be. I'm going to tell you what the dynamically typed language is, type system is. We're going to briefly go through garbage collection, concurrency, and I'm going to miss fault tolerance. So processes, I don't know if we had discussed that once or twice today, but Erlang loves processes, and they are lightweight, and they run in isolation. They have their own memory space, so no other process can corrupt a certain process memory. So only the process has access to its memory, which is great. They're provided their own CPU time, and Richard already talked about the preemptive scheduler. I like this picture because it's funny how we used almost similar metaphors. So yes, processes are cars, and there is, well, here missing policeman who says, now you go, and allows every process to have certain amount of CPU time. This allows us, first of all, since we have one scheduler per core, or one scheduler and one dirty scheduler, but we're going to talk about that later on. This allows us just by adding more CPU power to scale the system up. So it scales both horizontally and vertically. In the context of blockchains, we don't add more machines because if you add a machine in the cluster, in the Erlang cluster, then if that machine gets corrupted, the whole cluster gets corrupted, so you don't want to do that. But we'll discuss blockchains in a bit. So now garbage collection. The Erlang approach is still every process takes care of itself, and that comes with the garbage collection as well. Basically, every process has its own garbage collection and keeps its own garbage. There is no global garbage collection that once triggered, sits and blocks the whole system. Instead, every process, once it runs out of its space, that triggers the garbage collection, and if still the space is not enough to put a new object there, it grows. Yeah, so it's cool. You don't have to take care about that. I want to mention the typing system. So we have dynamic and static typing, and basically the difference between those is that the checks are being done either in compile time or in runtime. So if you try adding a string to an integer, it's a bad idea, and if you're using a static type system, the compiler is going to warn you about that. And in the dynamic case, this is going to explode in your face in the runtime, which doesn't sound good, but if you use dialyzer properly, it warns you. Tobias Lindell, one of the initial creators of dialyzer, loves to say that dialyzer is never wrong, but it still can get confused, and if it gets confused, maybe your code is wrong and can get improved. There is no strict definition regarding strong and weak typing, but if there was a definition, all attempts go around if you can circumvent the type system. So basically, in this example, you have two ints, and if you want to behave like they're floats, you can do that, and that's why the weak type system. What is important is that there is no right answer. It's just if it is your cup of tea or not, and it shouldn't be your cup of tea. So since we have two different dimensions of type system, we can plot them, and Erlang goes here, and JavaScript goes here. I don't know what to say about that. Now let's talk about blockchain. Okay. If you think a bit more abstractly about blockchains, they are only an append-only database. In databases we have transactions, but in blockchains we have different type of transactions. Basically, every change to the blockchain, every change to the record in the database is called a transaction, and happens through a transaction, and those are wrapped into blocks. The problem is that those blocks come in different time intervals. In some blockchains they come in a couple of seconds, in Bitcoin they come every 10 minutes. That means that you can update the database once every 10 minutes, and this is really slowly from the perspective of the database. So why would anyone use that in the first place? It's because it's trustless. Let's say you have a bank account, and the bank literally owns your transaction history, what transactions you had made. And if an admin of the bank decides to delete something, update your account, it's their right to do so, and you have nothing to say about that. With regards of the blockchains, you get to join a peer-to-peer network. You are peer to all other peers, and you can validate every transaction that's out there, which makes it trustless. You don't need a central authority to decide for everyone. From the perspective of distributed systems, it's radically different. I don't know what your experience with distributed systems is, but there are certain algorithms like Paxos and Raft and etc. And once we start talking about blockchain, they're all out of the window. In the blockchain context, any node can be malicious, not just corrupted, but actively trying to cheat other nodes and gain some advantage. That's why no one trusts anyone. That's why we don't use distributed Erlang in that context. The environment is radically different as well. In the traditional distributed system approach, you get a relatively homogeneous network. Like all your machines are running the same operating system, the same version of that operating system, and so on. In the context of blockchains, that's not the case. Our software runs on Windows, Linux, MacOS. It runs on the different architectures with regards of Apple Silicon, for example, and those we're going to be talking about full determinism later on, but those yield the same result. And we have zero control over who runs what where. Software versions is also a big subject. In the traditional approach of developing software, once you create a release, you have some strategy how this release goes to your servers, but you are in full control what gets updated and when. In the context of blockchains, that's definitely not the case. We produce a release, and maybe some people upgrade, maybe some don't, maybe some downgrade, and we have zero control. I have a battle story of that. We had identified some time ago a small bug that could harm a miner, could crash their node, because it was a nasty bug. And we have hotwired to miners, and we can tell them, hey, please upgrade. We are not going to say you what happened, but please upgrade. It's for your good. But we had a miner that we didn't know who that miner was. They joined the network as a peer, fully anonymous, and we have zero information who that miner is. So we sent them a transaction with a message like, please upgrade. Hopefully they will see that. Okay, so the blockchain has a, my Photoshop skills are mad. It has a set of rules. That's the protocol. Basically what is allowed on the blockchain and what is not. For example, if I have 3 coins, I cannot send 5 coins. I don't have that much. And the implementation is blind and simply applies those rules. It implements those rules saying that, yes, this is a valid transaction, or this is not a valid transaction, you cannot do that. And in order to do that, we need to be able to have full determinism and a canonical representation of certain objects. For example, the transaction, Alice sends a transaction to Bob. She needs to send a binary. She cannot send Erlang thumb because the protocol is language agnostic. The node can be implemented in any language, not just in Erlang. So she needs a way to serialize that transaction in a way that Bob can read the same transaction, decode it, deserialize it, and yield the same transaction at his end. Then they have to execute that transaction in the same way, yield the same result, otherwise the cryptographic checks will not match. So this is crucial. The same goes with blocks and blocks propagation through the network, because it's a peer-to-peer network where everyone can send messages and the other parties should be able to understand those. Erlang is really great with regard to that, as the combination of Beam and the runtime system provide us with full determinism. So we know, even if we're running different OTP versions, we know that this message is going to decode to this term. The crypto validation and hashing, we won't have time for that, but essentially imagine a class of functions that take a binary and yield a result, and you don't have a backwards way. So whatever goes to be validated as a cryptographic proof must definitely be the same thing that the other party considers to be the same block of data. It must be portable. Our software is running on different operating systems. We've discussed that. We support, I think, 4 OTP versions back in time, and the OTP team does a really great job of being backwards compatible. So they're not breaking anything with regards of backward compatibility without formally deprecating that and so on. So to be portable, we must be language agnostic. So you could, if you want to, implement the same protocol in JavaScript. Go ahead. And something that Erlang cannot help us is full backwards compatibility. Currently, our node is version 6.8.1. And we are allowed to ship protocol changes only when we break major version. So when we have a new major version, we can change the protocol. Otherwise, we can't. This means that our nodes all back to 6.00 are fully compatible. You won't get all the nice things that we've developed, but your node is going to sync successfully, hopefully. The whole thing is one big mesh of different nodes. We have miners, the green ones. we have non-miners, which are the blue ones, and on some of them we have applications running. This means that if that application produces a transaction and posts it to their node, this is going to propagate to its peers, and they gossip that transaction to their own peers. So we have a lot of peers, a lot of messages are flying, a lot of open connections are happening, and Erlang is really good with regards of processes and handles that really neatly. Yeah, let's move. Now, I know proof of stake is really trendy, and people love proof of stake. We're still proof of work, and for at least for the time being, we will stick to proof of work. But how do you implement proof of work? Basically, proof of work is solving a cryptographic puzzle, and that puzzle is CPU intensive. And thanks to our preemptive scheduler, we get to interrupt that process so it doesn't starve the CPU. Furthermore, Erlang provides nifs, which are small functions that are implemented in other languages, for example, C or Rust. They get their own schedulers. They're called dirty schedulers, which, because the runtime system can interrupt any process, as Ricard said, basically saying that you had enough CPU time, now move along, it's next process term. But you cannot do that if you're running a C process, because it doesn't understand C or Rust. So what happens instead is they have their own special class of schedulers, dirty ones, that can get blocked as long as they don't interact the whole system. So now a case study how Erlang helped us. In our protocol, we have smart contracts, and those are small programs that are implemented in our language. And everyone must execute those contracts locally and yield the same result. Basically, this is the brain of our system. And we had written that a couple of times, but Erlang was really helpful. So basically what the VM is, you get primitives, and this is a high-level virtual machine in which the primitives are transactions themselves. So you can compose them in arbitrary ways, and you're going to yield great results, hopefully. And they're all typed. Each operation has types, and it's type safe. So even though Erlang is dynamically typed, the virtual machine is not. It's statically typed, and you get warnings as you go. Furthermore, since different components of the virtual machine are loosely coupled, this allows us to add more or remove different components if needed. We haven't removed anything, but we can. And as a conclusion, the blockchain is really a moving target. It solves a lot of problems, hopefully, and imposes new problems. And this is constantly changing. And Erlang is really helping us do rapid development there. The loosely coupled components allow us to have a lot of different functionalities that cooperate together. Furthermore, we get full determinism because of the beam and the runtime system, and massive concurrency.
Hi, back to NIFs and their dirty schedulers. So you said because the Erlang VM doesn't understand, for example, the C code, it can't stop it and tell the next process to start. Yeah. So those dirty schedulers, they are unique for each language and implemented so that that language can understand the...
No. Basically, with the context of the intersection, the roads, you get a special road just for NIFs. And if that road gets jammed, a lot of cars, and there's traffic jam, this doesn't interact with the rest of the system. So you can have a really long running and computationally heavy process, but it runs in their own lane and doesn't stop the other cars in the other intersection. And they're running on the same CPU though. So you still will get saturation of the CPU, but other processes on the same CPU are going to be working fine.
All right, thanks.
I'm just wondering if you could say a tiny bit more about determinism in the context of running things like NIFs, and what do you mean precisely by determinism in this context?
No, not about NIFs. NIFs are small functions that yield a result. Basically, we treat NIFs in our context with mining as a black box. Basically, we feed it some numbers and it takes some.
But I could imagine if you run on a system with a large number of cores versus a system with a small number of cores, that could affect how long it takes for a particular NIF to terminate, and therefore that could affect the way that could affect the order in which things are accepted.
Well, not really. The thing is that it's a black box, but it's fully deterministic black box. So even if it takes longer, this blocks other processes. But the goal of mining is that we have one solution every, let's say, 3 minutes. So for 3 minutes, there are attempts being made, and we feed the black box, the NIF, with numbers, and it spits other numbers, or I couldn't find the solution. And the cool thing about cryptographic puzzles in the context of proof of work is that a solution is really hard to find, but it's terribly cheap to validate.
Yes, yeah.
And that's deterministic. Determinism, I meant, for example, if Alice sends Bob 1 coin, and that's a transaction, and that transaction must be encoded, sent to Bob. Bob is going to parse that, or the miner is going to decode that, execute it locally, and this is going to change the whole world, especially for Bob. And that must be fully deterministic, because others receiving a new block, they want to run the same checks as the miner did, and yield the same result. If the result is different, in the blockchain world, there is this thing, it's a really cool tree structure. It's called Markov-Patricia tree, where the nodes, the child nodes of a node form its value. And that goes all the way to the root of the tree. And changing one value anywhere in the tree yields a different result at the root hash.
Sure.
And that's what is being sent around. Basically, I applied this transaction, and this is the root hash that I got. And that must be fully deterministic. Otherwise, receiving a transaction and yielding a different root hash means that this is wrong. You did the computation wrong. I'm not going to accept that. And that could split the network. So determinism is crucial.
Okay, let's talk about it offline. I was wondering about, could one transaction get accepted more quickly on one machine than another? I don't know how much you're exploiting concurrency how much your nodes exploit concurrency, and so that I can imagine there could be effects to do with different levels of concurrency on different nodes, for example.
Our current implementation is strictly sequential, so we don't parallelize transaction execution.
Okay.
We're planning to do so, but we will parallelize only transactions that are fully independent from each other.
Okay.
So basically, Alice sending to Bob and Dave to Caro, they don't interact. But if Alice sends to Bob and Bob to Caro, those must be done in sequential.
Sure. Yeah. Okay. Thank you. Yeah.
So obviously, you send a lot of data around between different nodes and so on, right? Do you have your own binary format, like customized for this? Because I assume that there's some value in this, or is it just EBF?
No. There is this type of encoding called RLP, which specifies how you can produce a binary. And that binary, again, is deterministic, because if I send you that binary, you should be able to decode that and yield the same transaction locally. So we send binaries. We cannot send anything that is language dependent.
Right. But EBF is not language dependent. You can implement it in anything, right? So it's just a format. And if you wanted, you could use UBF, which I guess no one does, but it's really cool.
I don't know what that is.
It's the universal binary format. Joe Armstrong made this. It's fantastic. I have never used it though, so take that with a pinch of salt. But you know, it's really, when you see it, you're like, wow, this is great. I will never use this. But I was just wondering if it was general or if it was something custom for you that you have specified for people.
It is general, and it's really widely adopted across different blockchain projects.
Okay.
And there is a neat JavaScript implementation for that. So basically, me sending a transaction, you can validate that transaction in your browser if you want to.
Right.
And that's trivial.
Okay. Yeah. By the way, there's a TypeScript library for the Erlang binary format. I just want to say that.
Actually, we have a TypeScript SDK.
Yeah, hi. You mentioned that each process have its own garbage collection, but can you define what the process is? What is the scope of the process? Who spawn it? And in Erlang.
Well, the process, it really looks like, or at least feels like, an operating system process. So it really has its own space. It keeps track who spawned it, yes. But yeah, I don't know how to define a process. It's in memory space, it has its own stack and heap, but it also gets some CPU time when needed.
Okay.
Thank you.